Assalamualaikum and a very good morning to Dr. Halim. Today, we are from Group 3 going to present about the adsorption kinetic and thermodynamic. Before that, I'm going to introduce our members. My name is Latifah Binti Muhammad Hassan and my metric number is 207643.
My name is Siti Fatimah Binti Azman and my metric number is 208337.
Hello everyone, my name is Krishnasamy and my metric number is 207391.
My name is Syuhada Binti Muhammad Zailan with matrix number 206432.
My name is Nisa Binti Roslizam. My metric number is 205292.
So our presentation will be divided into these parts. So I will introduce about the adsorption kinetic and thermodynamic. So our topic will be focused on kinetic and thermodynamic of adsorption. Kinetic adsorption is the rate of adsorption directly proportional to the activity of the surface area. As the rate of adsorption increases, the activity of surface area of adsorbent also increases. This is the activation of adsorbent. The kinetic of adsorption is that there are only a limited number of sites on the surface. It can react which as the adsorbent being removed from the adsorbent will increase the rate of adsorption. There are two examples of kinetic adsorption. From example 1, charcoal acts as adsorbent in the formation of activated charcoal. Charcoal heats under 300 to 1000 degrees Celsius, so the adsorbent present in the surface of charcoal is eliminated. Thus, it forms activated charcoal. So the right picture shows that during adsorption, gas molecules stick onto the surface of activated charcoal. Next, example 2 shows the adsorbent metal such as nickel that break into small particles will increase the activation of adsorbent. Next is about the thermodynamic of adsorption. The most fundamental quantity in thermodynamics is the Gibbs energy. The relationship between the change in Gibbs energy, entropy, enthalpy is referring to this equation. Delta G equal to delta H minus T delta S. So as the entropy lower than 0 means negative value, it shows decreased randomness during the adsorption process because the value of initial entropy to the final entropy is decreasing. So the value of entropy is negative. Then, as the enthalpy is lower than 0, it shows the negative value, which it shows the exothermic reaction for spontaneous adsorption process, as the adsorption occurs to get stability by losing some energy. Thus, the energy of the product is lower than reactant, means the changing enthalpy delta H is always negative value. A spontaneous change is always accompanied by a decrease in Gibbs energy, which delta G is lower than 0 for all spontaneous processes of the adsorption process, while positive value shows non-spontaneous reaction. Next, from the table 17.1 shows the effect of enthalpy, entropy, and temperature on spontaneity. As the enthalpy and entropy are negative values, it becomes spontaneous at low temperature, while non-spontaneous at high temperature.
In order to determine kinetics and thermodynamics adsorption, there are three adsorption kinetics models that can be used, which are pseudo-first order reaction model, pseudo-second order reaction model, and intraparticle diffusion. So, I'm going to explain briefly about pseudo-first model, based on the assumption that the rate of change of solute uptake with time is directly proportional to difference in saturation concentration and the amount of solute uptake with time. It can be described by the following linear form, which is shown on the slide. The advantage of this model is that equilibrium adsorption capacity can be calculated from the model itself. Pseudo-first order can be determined experimentally, for example, the experiment that we have done before, in which is the adsorption of di-activated carbon. It is shown that by doing the experiment, we will achieve our data and interpret the data on a graph. Graph produced will be a graph of ln QE minus QT versus time, and from the graph itself, we could calculate the pseudo-first order with the help of the data from the experiment. Not as simple as that. We know that to produce the graph of ln QE minus QT versus time as shown on the slide, we need to find what is QE and what is QT. To find QE, we need to multiply the subtraction of initial concentration at initial time and the concentration at equilibrium with the volume of dye solution and divided it with the mass of activated carbon. While for QT, we need to multiply the subtraction of initial concentration at initial time and the concentration at time t with the volume of dye solution and divided it with the mass of activated carbon. As shown on the slide, that is the equation for us to find QE and QT.
Thank you, Nisa. So next, I will continue the presentation. Since Nisa already explained about the pseudo first order, so I will explain about the second adsorption kinetic model, which is pseudo second order. So pseudo second order kinetic model describe the adsorption of adsorbate onto adsorbent where the chemical bonding, meaning that the interaction between the adsorbate and the functional groups on the surface of adsorbent are responsible for the absorption capacity of adsorbate. It is based on equilibrium adsorption, which is it depends on the amount of adsorbate adsorbed on the surface of adsorbent and also the amount of adsorbate adsorbed at equilibrium. So the adsorption rate is depend on the adsorption capacity and not on the concentration of adsorbate, meaning that the concentration of adsorbate does not influence the rate of reaction. So next, we will move on to the purpose of this model. So this pseudo second order adsorption kinetic model is used to predict the order of the adsorption process and also to facilitate the evaluation of absorption capacity. The pseudo second order kinetic rate expression in linearized form is shown in this equation, which is T over Qt equal to 1 over K2 QE squared plus 1 over QE times T. Note that K2 QE squared is equal to H, where H is the initial adsorption rate, QE is the amount of adsorbed particle at equilibrium, and K2 represent the equilibrium rate constant at pseudo second order model. So this is a graph showing an example of pseudo second order kinetic for the adsorption of lead by eggshell and natural calcite at 20 degrees Celsius. So from the graph of T over Qt against T, the slope of the graph can determine the amount of adsorbate absorbed at equilibrium, which is QE. On the other hand, from the intercept of the graph, we can determine the equilibrium rate constant of the pseudo second order adsorption, which is K2. Pseudo second order kinetic model has been applied successfully to determine the chemisorption in several sorption systems. So as you can see from this graph, the R squared value is high, which is 0.999. So also in another research has proved that the removal of malachite green from aqueous media with a cyclodextrin based adsorbent followed the pseudo second order kinetic model with R squared value 0.9998. So also in another research has reported that the adsorption of basic dye onto phosphoric acid acidified soybean was best described with this model with R squared value of 0.999. So what can I say? In short, pseudo first order and pseudo second order are the two adsorption kinetic models that have been applied to a wide variety of adsorption systems, from biomass to nanomaterial as adsorbent and from heavy metals to pharmaceutical as adsorbate or contaminants. So next, I will pass this presentation to Kirtana to explain about intraparticle diffusion.
Next, I will proceed to the intraparticle diffusion part. So, what is intraparticle diffusion? Intraparticle diffusion is a rate parameter and characteristic of the rate of diffusion after the early stages of the adsorption. And the rate parameter can be determined for a number of variables including adsorbent mass, initial adsorbate concentration and particle size. Next, moving on to the intraparticle diffusion model. This model can be explained by an equation which have been shown in the yellow box. So the equation is Qt equals to KID square root of T plus C. First of all, Qt equals to amount of adsorbate adsorbed per unit weight of adsorbent, and KID is intraparticle diffusion rate constant, T will be the contact time, and C is the intercept or the constant which gives information about boundary layer. And the main information that we can understand from the C value is when the C is equals to 0, intraparticle diffusion is the sole rate limiting step and there is no initial adsorption behavior in an adsorption system. And when the C is not equals to 0, it indicates the presence of some degree of boundary layer control. Next, as we can see the figure, it shows the adsorption characteristic curves based on intraparticle diffusion model. And especially as we can see on the figure, Ri equals to 0.1 until 1.0, The Ri is the initial adsorption factor based on intraparticle diffusion model. And next, each adsorption system has its own specific characteristic curve. And the initial adsorption, weak or strong, can be also investigated using this intraparticle diffusion model. And lastly, the larger the intercept, the greater the boundary layer effect.
Now I'm going to explain about Van Hoff theory. Basically, Van Hoff factor can be defined as the ratio of the concentration particles formed when the substance is dissolved to the concentration of the substances by mass. The Van Hoff factor indicates the number of solid particles produced per formula unit that dissolve, the extent to which a substance associates or dissociates in a solution, described by the Van Hoff factor. The Van Hoff equation gives the relationship between the standard Gibbs energy change and the equilibrium constant. It is represented by the equation negative delta G naught equal to RT log E Kp. Now I'm going to explain about Van Hoff equation. The uses of Van Hoff equation is it has been widely utilized to explore the changes in state functions in a thermodynamic system. The Van Hoff plot, which is derived from this equation, is especially effective in estimating the change in enthalpy and also the entropy of a chemical reaction. As you can see in the green box, it is the Van Hoff equation where standard pressure is used to define the reference state. Then, as you can see on the slide, there is several Van Hoff equation from thermodynamics. Lastly, I'm going to explain about Van Hoff plot. For reversible reaction, the equilibrium constants can be measured at a variety of temperature. The graph plotted with log K on y-axis and 1 of temperature on the x-axis. It is widely used to estimate the enthalpy and also the entropy of a chemical reaction. As you can see from the slide, there's two types of graph plotted, which is graph of endothermic reaction and also exothermic reaction. As you can see, for endothermic reaction, heat is absorbed, making the net enthalpy change positive. According to the definition, slope is equal to the negative delta H over R. When the reaction is endothermic, delta H is greater than 0, so the slope value is lower than 0. Thus, the Van Hoff plot for endothermic reaction is always negative slope. For exothermic reaction, heat is released, making the net enthalpy change negative. This, according to the definition of the slope, equals to negative delta H over R. The delta H is always lower than 0, thus the slope is greater than 0. The Van Hoff equation for exothermic reaction is always positive slope.
So next, I will move on to the conclusion. In conclusion, there are several points that we have discussed. Firstly, we have introduced kinetic and thermodynamic adsorption, which adsorption is a surface phenomenon. Kinetic adsorption is related about activation of adsorbent, while thermodynamic about the Gibbs free energy, which delta G equals to delta H minus T delta S. Secondly, we also discussed the absorption kinetic based on pseudo first order and pseudo second order. Pseudo first order is able to calculate the equilibrium adsorption capacity, while pseudo second order is the adsorption rate is dependent on adsorption capacity. Next, intraparticle diffusion has been widely applied for the analysis of adsorption kinetic. Lastly, we also explained about the Van Hoff theory that describes how the substances in dilute solution obey the ideal gas law. So these are the references that we have used. I think that's all from us. Thank you.